I'm Rochan Sankar from Enfabrica. So I want to spend the last 10 minutes just talking about how this solves real problems over the next 12 to 18 months. So one of the key benefits of the aggregation and collapsing that we do is that you can enable wide fabrics with fewer hops. And fundamentally, GPU to GPU hop latency or just end-to-end latency is a big factor in exposed communication time, the amount of time it takes for a collective operation to complete. So, and that's not just measured nominal latency, it's latency with contention, which means tail latency actually matters. It's the stragglers that determine the completion time. And this matters not just for training, it can matter for any parallel type of workload that's going across GPUs. So the ACFS enables a 32x multiplier. Instead of a single port coming out of a NIC, you can do 32 ports of 100 gig coming out of us, which means that you can connect up to, as is shown here, if the blue boxes are basically 4 GPUs per ACF at 800 gig per, and we're connected to a rail of 32 switches. And then you look at that total population, that is a 4x increase over an 800 gig NIC, and then an 8x based on breaking an 800 gig port into 100 gig and actually going more diverse. What that enables at a data center level, which hasn't been done before, is to get to actually over 500,000 GPUs in just 2 layers of switching. For reference, almost all production AI clusters that are currently servicing up to about 24 to 36,000 GPUs are built using 3 tiers of network switches, plus the NIC, plus the PCIe switch. So we are trying to reduce that stack to get to more GPUs in fewer layers, which should improve, will definitely improve job performance. It'll increase utilization.
Is there a way you can put some quantification around that so people can understand when you suck out a layer, are we, what's sort of numbers, percentages, efficiency, something that we can wrap our hands around?
Yeah.
Put it in something.
We've put that in some of our NDA presentations because they're very specific to certain designs. But on average, the TCO optimization on the network side can be as much as 50 to 60% savings from current amount of spend on network.
Okay.
Which means you can buy more GPUs.
Yeah.
You can budget for more GPUs.
Yeah. I mean, but that's real. Well, it also means you can set the earth on fire a little bit faster.
But we've already saved some penguins, so I mean, we just give you back.
You can buy some penguin offsets.
Yeah.
We talked about resiliency, but just to examine how that occurs here, the multiplanar switch fabric is really key for doing that. Every GPU, no matter where it is, or every element that's attached to the right-hand side, has a way to basically multipath out nominally. But if there's a failure, if there is, like as shown as the red arrow, that port is down or that's flapping, we have a way to, in hardware, fail that over through the internal logic to the other members of that particular forwarding or interface group, and then for software to kick in based on the interrupt from that to be able to then do the optimal rebalancing. Because hardware can make a decision on the spot with no loss to be able to move the traffic over. But eventually, you'll get imbalances with how those things are done, because your optimal load balancing is going to try and distribute across all 32 or 8 ports. This is where ECMP can be a problem, because standard ECMP is a hash function. And if you actually take a big elephant for a GPU and you're like, hash it, it's going to hash to the same port. This is why Ultra Ethernet and other things have come up to try and load distribute that using transports that are in order for completions of packets, but out of order for data, meaning data can go whatever path it wants. We support the same. We actually came up with this before UEC in terms of how we would actually distribute traffic across ports. This is a major resiliency upgrade, and to show you how, I think we talked about this earlier. The scary data point.
When you're describing it as an implementation. You're shipping.
It's coming to a GPU cloud near you in 25.
There you
go. The amount that scaling is going to tax the resiliency of the network is, I think, as of yet, there's just a lot of fear and scrambling right now in terms of how this is going to be done when that goes optical. And it's one of the reasons why copper continues to be, people are trying to figure out ways to keep copper going to connect that first hop. Because the moment that scale grows larger and the radix grows larger, that you've got to centralize your first level switch, and then it's optical, which was actually the default design for this latest GB200, the first hop. NVLink was all copper within the rack, but it was optical to go to the first hop switch. The problem with that is that the failure rate, even if you take 5 years MTBF, again, 100K cluster, every 23 minutes will fail. And so our device, basically, instead of having an optical cable fail drive a GPU code path change, means the GPU never even saw it. It's just a slight degradation in bandwidth, depending on how much net overall, how skinny your links are. So major advantage, we think, and a major reason why people will go to higher radix coming out of the server. I think gone are the days where we'll see like just a single 400 gig port coming out of that. And we'll see a much more wider surface of bandwidth coming out of this. Doesn't this remind you of NVSwitch? Just on the network side?
A lot of parallels to prior things, but not all in one place.
So last 2 points I want to make: Gen AI, inference, and RAG, because a lot of this can be applied to training, especially when we talk about scale and we talk about resiliency and its impact on workloads. I think everybody generally accepts that the larger volume deployment of AI will be in inference fleets, in the actual scaling of services that are going to be actually using the models. Inference right now is a contained workload within one or more GPUs, leveraging entirely the HBM for its KV cache. And that's for LLMs. For DLRMs, there's a wider surface of data that's possible. Some of it leverages CPU DDR and the like. But ultimately, that's a very expensive data store if that's how this is going to scale in perpetuity. And what we have actually done, there are no words on this slide, and we're keeping some of the details of this design under wraps, but effectively what the ACFS can provide, in addition to just massive amount of bandwidth to hook in accelerators into the same network, is also a massive amount of bandwidth to make memory available as a shared tier to this. I mean, what are we seeing here? Basically, this is the pictorial representation of a memory area network.
Thank you. Excellent.
And what this provides is basically within a few microseconds access time to any accelerated compute server at the bottom tier. You can think of this as a tiered cache-driven architecture, just like most distributed workloads like Search and Spark are today, where your L1 is always going to be your local data store, the HBM. That's the closest memory, the highest access time. L2, adjacent GPUs. L3, the CPU DDR, but the CPU DDR is also local to a server. This is like the equivalent, and it could be DRAM, it could be storage, it could be them in different mixes. You could have some amount of bandwidth of DRAM as effectively a write-through cache to your storage. Now you can create effectively layers, and we think this is huge for RAG, because RAG is effectively going to be about 75% the retrieval part. And what this can do is effectively make the fleet more efficient. It's not about, bandwidth necessarily there. It's about how many individual GPUs do you have to wire in, because as you know, when you have a distributed database, affinity of access determines load. You have a service that has to respond within a particular latency budget. That latency budget will be different for different types of services. It's not all text to image or text to speech, which means that it has to generate really fast. Some of it, I like to make the conversations like, do I want who I'm talking to answer every question instantaneously, or do I mind if they say, let me think for a minute, if I can get you a better answer? That's especially most useful in the first computational phrase, which is your prefill context, what you give as prompts or what you give as inputs. That is also happens to be the most computationally intensive stage. If we can actually use a bunch of cheaper memory, and we're talking about more than an order of magnitude difference. We're talking about $80 per gigabyte versus $3 to $4 per gigabyte.
The H in HBM. Yeah.
Yep. We can cut down based on, like we show at the bottom in these graphs, the bounded latency of access for an aggregate query per second can be met with a much higher utilization when it's a shared memory element like what we have attached to us that is able to be accessed by multiple different workers. You can take the same concept to memcache and in-memory databases. Database acceleration can leverage a wide attached tier of memory to us over big fat network pipes, because guess what? Memory bandwidth is short on the CPU. If you turn network ports into memory ports using RDMA, you get a ton of memory bandwidth. Trade-off is latency. This is what we think the accelerated server architecture of the future will benefit from. So in summary, and I just got 45 seconds, so I couldn't have timed it better. What the ACFS does is it solves for the efficiency metrics that are going to matter in the next-gen data center. Bandwidth and throughput for the largest accelerated computing loads, wide flattened networks, and heterogeneity in terms of the type of compute. Could be talking about GPUs. I've said GPUs a lot. Could be custom accelerators. Could be memory. Could be storage. Any PCIe attached device today. Any server interconnect attached device in the future. Programmatic control of the fabric in terms of transport and congestion control. High radix throughput to any attached memory space with 40,000 copy engines that can move data around at extremely low latency. And with that, saving a lot of power. And that's
I have
what we have to present.
one simple question.
Yes.
You started off by talking about the model and hardware factor efficiencies that you were seeing on GPUs.
Yeah.
Do you have any offhand guess on where it would be using this type of range?
Where we'd be using this type of architect?
Yeah, yes.
I mean, our goal is to obviously insert into the largest clusters that are being built that are currently still being targeted for foundation model training, but also for inference fleets. And those are the ones where the MFU metrics are being collected,
Okay.
most frequently and with lots of eyes.
Okay.
The TCO models for that are eventually what going to differentiate the cost structure of different models.
Okay. What your message at the beginning said to me is if the highest HFU that we're seeing now is like 60 to 65%,
Less, but yeah.
less than 60 to 65%, that they've already made GPU density higher than any of the supporting hardware that's around it.
No, that's not the reason for that. It's efficiency in mapping, right? Because the way that a GPU architecture works, it's not, you can't just use every element that's in your matrix multiplication array. It's a software mapping to the available.
Okay.
So
Thank you.
that's the first step of why you get there. It's a software efficiency metric of compiler mapping to the underlying course,
Okay.
right? That's why it's capped. It's not because of there's excess
we should
flops
talk
just
more.
not being used.
We should talk more.